Hey, what's up, Mr. Sada here. Today we're going to be talking about the periodic table of elements and valence electrons. Let's get started here. All right, so to start off here, we have Dmitri Mendeleev. He is credited with founding or creating the foundation for our modern periodic table. There were periodic tables before his, but his is the one that we use as the foundation for our current table. Not too much information we're going to go into depth about him, but he did model the game after the card game, Solitaire, and he was able to make really accurate predictions about elements that weren't discovered yet because of the way he set up his periodic table. All right, so when we look at our periodic table, we can see that all of the table, all the elements are organized in a particular way, and we can learn a lot of information about an element based upon its position in the periodic table. So, for example, you could predict physical and chemical properties in an element, or with which elements one element will react with. Right? So understanding how the periodic table is organized and planned out will help you determine basic information about our known elements without having to memorize anything. So as long as you can know the trends and the patterns, you don't have to memorize anything about the table. All right, so let's look at this here. So on the periodic table, there are lots and lots of different elements, and these elements are put into these boxes here. The elements are organized in the table according to their atomic number. It's usually found at the top of the square. So here's hydrogen. Its atomic number is 1. If you remember in one of our previous lessons, the atomic number is equal to our number of protons, which is equal to the number of electrons in a neutral atom. All right, so for instance, hydrogen's atomic number is 1, so it has 1 proton and 1 electron. The atomic number is unique to that element, and no two elements have the same atomic number. So hydrogen is only ever going to be 1. For example, helium is always going to be 2. No two elements have the same atomic number. Each one has its own unique number. All right, so what's in the square? Lots of different things, but usually it is the atomic number up in the right corner, the symbol for hydrogen is H, the atomic mass, that's this number down here below the atomic symbol. The number of valence electrons sometimes, that's down here in the right corner. The state of matter that element exists at room temperature. So for example, in this bottom left corner, hydrogen is a gas. Sometimes there's more information, sometimes there's less, but usually it'll contain some or all of this information. All right, so the elements are divided in the periodic table, can be divided into 3 big categories. They are metals, that's all of these blue squares in here are all considered to be metals. These green ones, which are non-metals, and then metalloids, which are like they're like the transition zone in between something that's a metal and something that's a non-metal. And metals and non-metals have special properties, and we'll talk about that in a future lesson. All right, so elements in the periodic table are also grouped into families or columns, and each of the elements in their group or column, they have similar chemical properties. So up and down, these are columns or groups. All right, so columns, also called groups or families. Elements in each family have similar but not identical properties. So for example, lithium and sodium, potassium are all members of the 1A family. And a characteristic that they have is they're all soft, white, and shiny metals. Right? All elements in a family also have the same number of valence electrons. So that's the number of electrons in our outer shell. So for example, lithium, sodium, and potassium all have 1 valence electron because they're in group 1A. Right? The elements are also categorized into periods or horizontal rows. So going across these are periods. Elements and periods do not have similar properties. All right, so each horizontal row is called a period. They're not alike in any way, the elements in a period. In fact, the properties are very different as you go across a given period or row. The first element in the period is usually an extremely reactive solid. For example, potassium by itself reacts violently with water, and the last element in the period is usually an inactive gas. We call those noble gases. All right, so question for you here. So that's a little background about a periodic table. Now I want to pose this question to you. What does your outer shell of clothing say to other people about who you are and what you're about? So for example, me as a teacher, I go into work every day. I wear a dress shirt, I have a tie, it tells other people that I'm a professional and that perhaps if I'm working in a school, that I'm a teacher, right? So in a similar way as to like we wear our clothing and it tells other people about us, the outer shell of an atom tells us a lot about what the atom is like and what its properties are. All right, so some background info here we've talked about before. Atoms are composed of protons, neutrons, and electrons. The protons and neutrons are found in the nucleus, and our electrons are found in our electron cloud. The information's over here on the side. The electrons, they occupy energy levels that surround the nucleus in the form of an electron cloud. So our protons and neutrons are in a really dense sphere in the center of an atom, you can think of it. And then the electrons are all buzzing around that nucleus in an electron cloud. Right? The electrons are involved in forming chemical bonds. Those electrons which are involved are called valence electrons, and those are the outermost electrons in our electron cloud. They're like the outside electrons. All right, so for valence electrons, the number of electrons in an outer shell can range from 1 to 8. They have the highest energy level and they're held the most loosely. The number of valence electrons in an atom of an element determines many properties about that element, including the ways they can bond with other atoms. Elements and groups have the same number of valence electrons. So, for example, all of the group 1 elements have 1 valence electron. All of the group 14 elements have 4 electrons. And we'll look at that more in a second. All right, so chemical bond stability. Atoms of most elements are stable. They're less likely to react when they have 8 valence electrons. We call that a complete octet. Octet, you can see in that word there, like octopus. Oct means 8. An octet is a full set of 8. Right? So atoms usually react in a way to make themselves more stable. So they want to get to those. If 8 valence electrons makes them stable, makes them happy, they want to react in a way with other atoms to make themselves more stable. And to help you remember that, look at a reminder here. So think about how you feel after you eat a big meal. Would you want to eat another meal? No, right? So you ate and you're full. So just in the same way, when atoms have 8 valence electrons, they're full and they're happy. Just like you ate and you're full and now you're happy. All right, so how can an atom become more stable? So we want to increase the number of valence electrons to 8. So in order to do that, we have to gain electrons. Again, following our octet rule here, so atoms tend to combine in such a way that they have 8 electrons in their valence shell. They want to have 8 electrons in that outer shell. So they can either gain electrons or they can give up loosely held electrons. And when they do that, this can form a chemical bond, which again is the force of attraction that holds 2 atoms together. It's usually done through the sharing of electrons. Right, so there's 2 ways which we can set up. There's 2 ways that we can set up our electron configurations here. Configuration is just a way that we set something up. So for example, we have a Bohr diagram which shows all the electrons that an element has. If you look down here on the left, this is a Bohr diagram. In the center we have our nucleus, and all these rings outside, these are called shells. And you can see my number of electrons change as I go outside. My first shell has 2, my next shell has 8, and then my last shell, that's my valence shell, I have 3 electrons in my valence shell for aluminum. Another way to set up an electron configuration is with a Lewis dot diagram, which only shows the number of electrons in the outer shell. So here's my Lewis dot diagram for aluminum. You can see here I only have 1, 2, 3 electrons. I have 3 valence electrons for aluminum. And I can see the same thing on my Bohr diagram. I can see I have 1, 2, 3 electrons. So my Bohr diagram gives me more information than my Lewis dot diagram does, but both are ways that we can use to show our electron configurations for given elements. All right, so let's go over how to draw Bohr diagrams really quick. So first, you want to find the element that you want to draw on the periodic table. You're going to look for the atomic number and the mass number. And from this, you can determine the number of protons, neutrons, and electrons. I'm not going to go too much into detail because we've done this before. So for example, we have helium. How many protons does it have? I look up in the corner my atomic number. It's 2, so I have 2 protons. electrons. My protons and my electrons are equal in a neutral atom, so I have 2 electrons. And then my mass, my atomic mass down here is 4. If you remember, our atomic mass is our number of protons plus our number of neutrons. So if 4 is my atomic mass, 4 minus 2 is 2 neutrons get left over. 2 neutrons plus 2 protons equals 4, my atomic mass. Right after that, we're going to draw the nucleus of the atom by writing the number of protons and neutrons inside a circle, like it is below. So here's my nucleus, and inside I draw my protons. So I'll make P, my protons equal to 2, and N, my neutrons equal to 2. Right? After that, we're going to have to place our electrons as dots onto the rings as follows. We're going to work mainly with 3 shells here. So our first shell, also called the K shell, can hold 2 electrons. The second shell, also called the L shell, can hold 8 electrons. And the third shell can also hold 8 electrons. So here's my loose dot diagram on the side. I'm sorry, my Bohr diagram on the side. I have my nucleus in here. And then I only have 2 electrons for helium. So I make 1 shell and I put 1, 2 electrons on it. All right, so pause the video right here and try drawing this one out. I'm going to move on to the next slide. So pause here, draw yours, and see if it looks like mine over here. Right, so it should look something like this. I have my nucleus drawn here with my number of protons and my number of neutrons. And then I drew 2 shells here, 2 in the first shell, 1, 2, and then 3 in the outside shell. Right, so for my total of 5 electrons. So we can make a prediction here. How many more electrons are needed to make nitrogen a stable atom? Well, let's count how many valence electrons we have. We have 1, 2, 3 valence electrons. In order to be stable, we want 8 valence electrons. So 8 minus 3, we need 5 more electrons to make this atom nitrogen stable. All right, so how do we find out the number of valence electrons? Well, you can draw the Bohr diagram every time, but that's a whole lot to do. So instead, you can follow these trends here. So for example, our group 1 elements all have 1 valence electron. Our group 2 elements all have 2 valence electrons. 13 has 3, 14 has 4, 15 5, 16 6, 17 7, and 18 8, except for our topmost group 18 element, which only has 2 valence electrons. All right, so you can use these patterns or trends rather than having to draw the Bohr diagram each time. All right, so for electron dot diagrams, an atom's valence electrons are shown as dots around the symbol of an element. Each dot stands for 1 valence electron, so this is where we're talking about our Lewis dots. So for example here we have carbon. It has 4 outer shell electrons, 4 valence electrons, so I go 1, 2, 3, 4. Boron here has 3 outer shell electrons, 3 valence electrons, so I go 1, 2, 3. Nitrogen here has 7 electrons in total, but only 5 outer shell electrons. So I go 1, 2, 3, 4. And the second time around, we go around, we get a buddy. So we get 5. 1, 2, 3, 4. Oh, I'm sorry. 1, 2, 3, 4, 5. All right, so let's make a prediction here. How many more electrons are needed to make a nitrogen atom stable? If we have 5 outer shell electrons, we need to get to 8 to be full. 8 minus 5, we need 3 more valence electrons to make our nitrogen atom stable and happy, right? That wraps it up for the periodic table and valence electrons. I know we covered a lot of information, but I'm happy that you watched. If you have any questions, feel free to message me, and I hope that that helps you out, and I'll see you in the next video.